So in this video, we're going to look at systematic procedures for drawing the Lewis structures of molecular compounds. So this is a systematic process. It involves sort of 5 or 6 steps, and it's kind of easy to get correct if you learn those steps and follow the steps through. So in the Lewis structure of a molecule, what we're going to do is we're going to assume that all of the valence electrons for the atoms that are present are available to be shared. So, and then when they share these electrons, what the atoms are going to attempt to do is make sure that every atom in the molecule obtains a stable noble gas-like octet, with the exception of hydrogen, which is happy if it can obtain 2 electrons like helium. So the very first step in drawing the Lewis structure of a molecule is to add up the total number of valence electrons available to form all of the bonds and lone pairs in the molecule. Now this is a fairly easy procedure because the number of valence electrons for a representative element is just equal to the group number. So the group number of carbon is 4A and the group number of chlorine is 7A. So when we're adding up all of the valence electrons in the carbon tetrachloride molecule, we get 4 electrons from the carbon, and then we've got 4 chlorine atoms, each of which has 7 valence electrons. So adding all of that together, 4 times 7 is 28, plus 4 gives me 32 valence electrons, which I'm going to spread over these 5 atoms in such a way that every atom gets a octet. So in this case, there's no hydrogen atoms, so we understand that every atom is going to need 8 electrons. Okay, so the second step is to decide the arrangement of atoms in space, how they're going to be connected to one another. And for us, what we're always going to have is one central atom, and then the other atoms are going to be connected to that. So there are a few guidelines that can help. So we're going to have the one central atom and then a bunch up to 4 outer atoms. So what we know is that hydrogen will always be an outer atom. And the reason is hydrogen has just 1 valence electron, so it can only form 1 connection to another atom. So it can't be in the middle and form multiple connections. So hydrogen, we're always going to put it on the outside. And from there, deciding the rest of the sequence is relatively simple. The element with the lowest group number will be the central atom. And the reason is because that's the one that's going to need to make the most bonds to get an octet. So if I look at nitrogen, which is in group 5A, it needs to make 3 bonds to form an octet. So it makes sense that it's going to have 3 atoms attached to it. But if I look at something like oxygen, which is in group 6A, it has only 2 unpaired dots, so it's happy if it can make 2 bonds. So as a result, we're going to put the atom that has the greatest need to make bonds in the middle. Okay, so the one with the lowest group number, so 5 is lower than 6A. Now occasionally you'll get a molecule where both atoms are in the same group. If that's the case, we're going to put the one that is lower down in that group in the middle. So there are a bunch of compounds that have sulfur and oxygen in them. So let's say sulfur dioxide. And if we look at the periodic table, both of these guys are in group 6, but sulfur is below oxygen. So we know that sulfur is going to go in the middle and the oxygens are on the outside. So it's a pretty simple kind of procedure, okay? Another way of thinking about this is lower group number and then higher period corresponds to a larger atom, or it also corresponds to the atom with the lowest En, or we can say the biggest radii goes in the middle, because remember, electronegativity decreases that way and radii increases that way. Okay, so for our example molecule of carbon tetrachloride, carbon is in group 4A, chlorine is in group 7A, so 4 is less than 7, so therefore carbon goes in the middle and chlorine goes on the outside. Okay, so nothing is connected to one another at this point. So our next step is going to be to connect everything by, at the very least, single bonds. And they just have to be connected by single bonds, don't they? Otherwise, we don't have a molecule. So everything needs to be connected to the central atom by at least a single bond. And every single bond uses up 2 electrons. So we had a total of 32 electrons to form the molecule, and then we've used 4 times 2 electrons to create those single bonds, and that leaves 24 electrons left to finish everything else off. So once we've got our central atoms and outer atoms identified, we're going to connect those together with single bonds, and then we're going to subtract that number of electrons that we used to make the single bonds from the total. So our third step is to connect the outer atoms to the central atoms via a single bond, and then subtract the electrons that we used from that total that we calculated in the first step. Okay, so we've done that and we've got 24 electrons. What we're going to do now is we're going to add lone pairs to every atom until we've used up all of these 24 electrons. Now, when we do this, we're going to stop adding lone pairs to an atom once it gets an octet. So our next, and then we're going to work from the outside towards the center until we run out of electrons. So the first thing that we're going to do now is we're going to complete the octets on all of the outer atoms and subtract the number of electrons that we used from the total. So we're going to add lone pairs to each of our outer atoms until they all have an octet, and then we're going to subtract the electrons used from the total. So every chlorine had a share of 2 electrons from the bond. So we need to add another 6 as lone pairs. So we're going to add 3 lone pairs to every chlorine. So we're going to add a total of 6 electrons to every chlorine to finish off the octets on the chlorines, and then that'll give them a total of 8 electrons around them, and everybody's happy. So 24 was what we had left after making the bonds, and now we're going to subtract away 6 electrons on each of the 4 electrons, so that means we've got no electrons left. So at this point, if we don't have a molecule where every atom has a complete octet, we can't add any more electrons. All we can do is move electrons around. So our fifth step, and we don't need to do it in this case, is if we had any electrons left over after completing the octets on the outer atoms, we would put them on the central atom. But in this case, we had 0 electrons left, so we don't need this step. Then the final step is we have to move electrons around to make sure that every atom has an octet. Now we know the outer atoms have octets because we made them that way. What we have to check is, does the central atom have an octet? And if it doesn't, what we're going to do is we're going to move in lone pairs from the outer atoms and make them shared pairs until it has an octet. Now, in our case, the carbon atom here has a share of 2, 4, 6, 8, so it's already got an octet. So our final step, check if the central atom has an octet. If it doesn't, bring in lone pairs and turn them into doubles or triple bonds until the central atom has an octet. Now, in our case, when I check the central atom, 2, 4, 6, 8, it's already got an octet, so I don't need to do this step. It's not needed. Okay, so that's it. I think in your book it describes it as 5 steps. It kind of pushes a couple of them together. That's fine. I think steps 2 and 3, it kind of pushes them together. But effectively, you have to do all of these steps to ensure that you don't use up more electrons than what you're meant to, and also that you have every atom with an octet. Now, when you think you've got a Lewis diagram, there are 2 things that you should do. One is check the electron count. So we were meant to use up 32 electrons. How many have we used up? 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, 32. So the electron count is correct. And then check octets. So every atom should have 8 because none of these guys are hydrogen. So the carbon, 2, 4, 6, 8. Carbon is good. all of the chlorines have the same bonding pattern. So if I check 1, I know I'm going to be right on all 4 of them. 2, 4, 6, 8, the chlorines are good. And all of the chlorines are exactly the same. 2, 4, 6, 8, 2, 4, 6, 8, 2, 4, 6, 8. They're all good. All 4 chlorines are good. There's no way that this molecule doesn't have the correct Lewis structure. Okay, so that's really it. And this is very important to check the electron count at the end and also to check that every atom has a complete octet. If either of those things isn't right, you have an incorrect Lewis diagram. So let's go to an example where we need to make some double bonds. So we're going to write the Lewis structure for carbon dioxide. So carbon's in group 4A and oxygen is in group 6A. So when I count up the valence electrons, I get 4 for the carbon, and then I've got 2 oxygen, each of which has 6 valence electrons. And I'm just getting this from the periodic table, right? So 4 plus 12 gives me 16 electrons. Now, what atom's going to go in the middle? Is it carbon or is it oxygen? Well, carbon is in group 4A, oxygen's in group 6A, so the element with the smaller group number goes in the middle, and then the outer atoms are going to be what's left over. So carbon is the central atom, and then the 2 oxygens either side as the outer atoms. Now, the outer atoms need to be connected to the central atom by, at the very least, single bonds. So I'm going to put in place 2 single bonds, each of which uses up 2 electrons, and I'm going to then subtract those electrons from the total. So 16 minus 4 gives me 12 electrons left to finish off the molecule. So now what do I have to do? I have to complete the octets on my outer atoms. At the moment, my oxygen has a share of 2 electrons, so it's going to need another 6 electrons added to it, and each of them are going to need that. And then I need to subtract that from my total. So minus 2 times 6 electrons, and then I've got no electrons left. So what that means is if things don't have an octet at this point, then all I can do is move around those electrons that are already there. I can't add any more electrons. So step 5 is to place any leftover electrons on the central atom, and there aren't any leftover electrons, so step 5 is not needed. And then step 6 is to have a look and see if our central atom has an octet. And if it doesn't, we're going to have to move electrons into bonds until it does. So that's where we were starting. And at this point, the carbon atom has a share of 4 electrons, 2 from each bond. So I've got to add in another 4 electrons. So what I'm going to do is move in 2 electrons there, and then that bond is going to become a double bond. And then I'm going to move in 2 electrons here, and that bond is also going to become a double bond. So what I'm left with is this guy with 2 double bonds to the carbon, and then each oxygen has 2 lone pairs. So if I check everything now, remember what we had? We had 16 electrons to begin with, so we're going to check electron count, and we've got 2, 4, 6, 8, 10, 12, 14, 16. So electron count is correct, and then now we're going to check that the octets are okay. So we've got carbon, 2, 4, 6, 8, because every line represents 2 electrons. And then the oxygens, we've got 2, 4, 6, 8. And both of the oxygens are the same, 2, 4, 6, 8. So as long as every atom has an octet and we've used up the correct number of electrons for the molecule, then we're okay. So that's cool, right? So once you start doing a bunch of these, and you'll have the opportunity to look at them and also to create them in Alex, you start noticing a few things. Halogens, which are in group 7A, they all have a Lewis dot diagram that looks like this, and they tend to form 1 bond. Oxygen, that's in group 6A, generally, it has 2 octet vacancies, generally will form 2 bonds. That's going to either be 2 single bonds or, like in the case of carbon dioxide, a double bond. Nitrogen atoms are in group 5A, and they most commonly form 3 bonds with 1 lone pair. Now, it could be a double and a single, or it could be 3 singles. They have 3 octet vacancies. And then carbon atoms, most of the time, they form 4 bonds, and they're going to be like so. So that's what's happening there, right? So, the octet vacancy rules kind of really help out. Now, we will see exceptions to these rules. If we see exceptions from the general pattern, that's okay. You just want to kind of like double check that your electron count is good and that every atom has an octet. Okay, so here are some examples. And this one is a little different because it's a polyatomic ion. And what makes a polyatomic ion different is we have to add in extra electrons to account for the charge if it's an anion. So anion, you got to add electrons, and I'll show you how to do that in a moment. And for cations, you got to subtract electrons, because ions form when neutral atoms or collections of neutron atoms lose or gain electrons. So this is an anion, so that's going to affect how we count up the number of valence electrons that we're going to start with. So carbon is in group 4A. That's not how we write 4A, is it? 4A. And then oxygen is in group 6A. So we've got 2 carbon atoms, so 2 times 4, and then we've got 4 oxygen atoms, so 4 times 6, and then here's where the charge comes in. This is a negative charge, so we're going to add 2 electrons to account for the charge, and that's important. Now, if this was a positive charge, say plus 2, then we'd be subtracting 2 electrons, but it's not. It's a negative charge, right? So we've got to make sure that we add in 2 extra electrons. So we've got 8 plus 24 gives me 32, and then we've got another 2, so that gives me 34 electrons. Okay, so that's step 1 done. All right, step 1 is done. So that's it. All this question asked was how many valence electrons are there, and the only thing that's a little tricky about this is we have to add in an extra 2 for the charge. All right, let's have a look at this one. It says decide whether the proposed Lewis structures are reasonable. Remember, there's 2 things that we want to check, is the electron count and that every atom has an octet. So that's what we're going to check in every case. So carbon is in group 4A and oxygen is in group 6A. So carbon monoxide, we've got 1 carbon, so that's 4, 1 oxygen, that's 6, it gives me 10 electrons. So the first thing that I'm going to do is count up the number of electrons. So I've got 2, 4, 6, 8, 10. So it's good on the electron count. The next thing I have to do is check the octet. So we've only got 2 atoms here, carbon and oxygen. So carbon has 2, 4, 6, 8 electrons around it, so that's good. And then the oxygen has 2, 4, 6, 8 electrons around it, so that's good as well. So this is a good Lewis structure. Now, something to be aware of is that it's kind of not following the trend, right? Because carbon generally likes to make 4 bonds, and oxygen generally likes to make 2 bonds. But it's okay because, the average of 4 and 2 is 3, and that's really the only way that we're going to get this. So occasionally you will see that it doesn't follow the pattern of octet vacancies. Okay, let's move on to the next one. First thing to check is the electron count. Second thing to check is that every atom has an octet. Now, what we want to be aware of in this case is that it's not actually every atom has an octet. It's got hydrogen in there. So hydrogen is going to be happy with 2 electrons because helium is its nearest noble gas. So let's do the electron count. Hydrogen's in group 1A, so that is 1 electron. Carbon is in 4A, so that's 4 electrons. And then nitrogen is in 5A, so that's 5 electrons. So that gives me a total of 10 electrons. So do I have a count of 10 electrons? 2, 4, 6, 8, 10. Let's double check that. 2, 4, 6, 8, 10. So it does have the correct number of electrons. But now we need to check octets. Hydrogen has a share of 2 electrons, so it's happy. Carbon has a share of 2, 4, 6, 8, so the carbon is happy. Nitrogen, 2, 4, 6, the nitrogen is unhappy. So this is not a valid Lewis structure. And the reason that it's not a valid Lewis structure is that it does have the right number of valence electrons, but doesn't satisfy the octet rule. There it is there, right? Now, what atom doesn't satisfy the octet rule? It's nitrogen. Okay, now sometimes you might have more than one nitrogen or more than one carbon that doesn't satisfy it. If that's the case, you're going to put both of the occurrences in separated by commas. And it gives you a little hint about that at the bottom there. All right, let's move on to the last one. Now, the last one is a polyatomic anion. So we have to remember that we have to add in electrons equal to the number or the size of the negative charge. So let's give that a go. So we've got chlorine and oxygen. Chlorine here, oxygen here. So chlorine is in group 7A. There are 1 of them. Oxygen is in group 6A. There is 1 of them. And then there's this negative charge. So we add in +1. And that gives a total of 14 electrons. So we check 2 things, right? One is electron count. So do we have 14 electrons? 2, 4, 6, 8, 10, 12. So it is no. Let's just double check that. 2, 4, 6, 8, 10, 12. We don't have 14 electrons, so it has the wrong number of valence electrons. The correct number was 14. Okay, so in this problem, we're asked to predict the single bonded molecular compound formed by 2 elements. So it's all going to be about looking at the Lewis dot diagrams of the elements and deciding how they're going to combine. So we've got hydrogen over here in group 1A, so it has 1 dot. And then we've got bromine over here in group 7A, so it has 7 dots. And how I like to organize the dots is so that the unpaired dot is facing the other atom. So bromine with its 7 dots there, it's got 1 unpaired. Hydrogen with its 1 unpaired, what are they going to do? They're going to come together like that, and there's going to be a single bond between the 2 atoms and 3 lone pairs on the bromine. So here we are. This is going to be the compound that is formed. So the element will form a molecular the element pair will form a molecular compound because we have 2 nonmetals. So there we go. And the chemical formula of that compound will be HBr. And then finally we have to name it. And if you recall, when we name compounds where the formula starts with hydrogen, we name it as though it was an ionic compound. So it becomes hydrogen, no mono required. And then because we're naming it like a ionic compound, we don't have to put mono for the bromine. We just change the end of the bromine to ide, so it becomes bromide. Hydrogen, bromide. So compounds whose formulas start with hydrogen are named as though they are molecular compounds, even though they're covalent compounds. Oh, sorry, they're named as though they were ionic compounds, even though they are molecular compounds. So that one's going to be called hydrogen bromide. A little bit tricky that, because you have to remember that rule about the naming. Most molecular compounds we're going to name using the Greek prefixes, where we give the name of the first element followed by the name of the second element with the ending changed to IDE, and then we insert the Greek prefixes. Now the next pair of elements is calcium, which is a metal, and a nitrogen, which is a non-metal. So these guys don't form a molecular compound, so you kind of get an easy ride on that one. So no entry for row number 2. Now row number 3, we've got carbon over in group 4A, it's a non-metal, with bromine again in 7A, so we've got 2 non-metals. So carbon is in a lower group, and then bromine. So carbon is going to go in the middle, and it's in group 4A. So it's got 4 dots around it. Now bromine is in group 7A. So it has 7 dots around it. And so you can see it can pair up with one of the dots of carbon. So there we go. So when we look at it this way, we can see how these guys are going to pair up, can't we, right? Like that. So in total, there's going to be 4 bromines around the central carbon. There we go. Look at that. And so what we're left with is a compound where the Lewis diagram looks like that. So this is kind of cool because before we were predicting the formula, the product of the reaction between a metal and a non-metal, and now we're in a position where we can predict the formula of a compound combined that forms when 2 non-metals combine. So this will form a molecular compound because we have 2 non-metals coming together. The chemical formula will be CBr4. And the name of it, we give the name of the first element unaltered, so that's just carbon. Then we give the name of the second element, but we're going to change the ending to IDE. So it's going to be bromide. And if you're uncertain of the stem names, remember that there's a list of them in your textbook, bromide. And then we apply Greek prefixes with a couple of rules. The one is that we don't need to give mono for the first atom. So we don't need to say monocarbon. It's understood that there's one. For the bromide, we're going to give the prefix for 4, which is tetra. So this is going to be carbon tetra bromide. Carbon tetra bromide. So making a little list of the naming rules for compounds that you can easily kind of, hopefully it's in your notes, but you can just pull that up very quickly, especially if those notes, if you save them with PDFs with meaningful names, then that's going to help you find that information when you need it. So that's the real value of your notes, is that that information is available for you when you're doing a quiz or a test. Okay, let's have a look at this one. It says predicting the compound formed by 2 main group elements. Main group is another way of saying representative. So what we're looking for, is it ionic, molecular, or neither? So remember that ionic is going to be a metal plus a non-metal, right? And then molecular, which is another way of saying covalent, that's going to be 2 non-metals. Now, what don't we have in here? What about if we had 2 metals coming together? That's going to be neither of those things, right? So that's what we're looking at there. So hydrogen and iodine, hydrogen's a non-metal, iodine's a non-metal, it's going to form a molecular compound. Carbon is a non-metal, chlorine is a non-metal, it's going to form a molecular compound. Potassium is a metal, and chlorine is a non-metal, so it will form an ionic compound. Now, we know that we need to look at Lewis symbols for molecular compounds to be able to figure out the formulas. So, the Lewis symbol for hydrogen has 1 dot, that is unpaired, and then for iodine, because it's in group 1A, and for iodine, which is in group 7A, we're going to have 1, 2, 3, 4, 5, 6, again, 1 unpaired dot. So these guys are going to come together in a 1-to-1 ratio, and those unpaired dots are going to end up being shared. Here we go. And by coming together 1-to-1, every atom gets a noble gas configuration. So the chemical formula here will be HI, and the name would be hydrogen iodide. We would name it as though it was an ionic compound because the formula begins with hydrogen. All right, the next one, we've got carbon and chlorine. So carbon's in group 4A and chlorine is in group 7A. So carbon has 4 octet vacancies and chlorine in group 7A has just the 1. So what I hope that you can see is that carbon's going to go in the middle there, and then there's going to be 4 chlorines situated around it, all right? And then their unpaired dots there, you think of them as a hand grasping out to grab another unpaired dot and become paired up. There we go, like that, all right? So those guys are going to end up forming, let's put it like over on a weird angle over here, carbon with 4 chlorines attached, and each of the chlorines has a lone pair on it, or 3 lone pairs on it, I should say. So there we go, each chlorine has 3 lone pairs on it. So what's the formula here? It's CCl4. CCl4, there we go. All right, so potassium and chlorine. We know that potassium's a metal, chlorine is a non-metal, so these guys are going to form an ionic compound. Now, the ratio of the different ion types is going to be determined by their charges. Now, for main group or representative elements, we can always get the charges of the ions from their positions in the periodic table. So, here's our periodic table, and chlorine is over here in group 7A. And everything in 7A forms a -1 anion. And then potassium is over here in group 1A, and everything that's in 1A forms a +1 cation. So potassium forms +1, chlorine forms -1. You can see the charges are equal and opposite, which means that these guys come together in a 1-to-1 ratio, and the formula of our compound is just KCl, which we would call potassium chloride. This potassium ion doesn't need Roman numerals because it's in group 1A. Alright, so that concludes this section on writing Lewis structures of compounds. I hope you found it helpful. Please reach out to me if you're having any difficulty with the content.